Welcome to the lesson on polynomials in one variable. At the end of this lesson, you will be able to identify polynomials and non-polynomials, define a polynomial in one variable, state the general form of a polynomial in one variable, determine the degree of a polynomial in one variable, and determine the zero of a linear polynomial. Look at the expressions on the screen. Can you identify the polynomials in this set of expressions? A polynomial is an expression containing one or more terms where coefficients are not equal to 0 and exponents of variables are whole numbers. A polynomial can have one or more variables. Let's review again the expressions that we saw earlier. As you can see, the expressions are categorized as polynomials and non-polynomials. So, what's the main difference that you can see between expressions in the two categories? The terms of the polynomials have whole numbers as exponents, while the terms of non-polynomials have fractions or negative numbers as exponents. If you examine the list of polynomials further, you will see that some of them have a single variable x, while others have two variables, x as well as y. A polynomial that contains one variable is known as a polynomial in one variable. A polynomial in one variable can be represented as p of x, q of x, or f of x, and so on, where x is the variable. For example, p of x is equal to x squared plus 2x plus 1. The general form of a polynomial in one variable is p of x is equal to anx to the power of n plus an minus 1x to the power of n minus 1 plus and so on till a0, where an minus 1 and so on till a0 are real numbers. The exponents of terms are whole numbers. N, the highest exponent, n, is the degree of the polynomial where an is not equal to 0. You can name a polynomial on the basis of its degree. A polynomial of degree 1 is called a first degree or linear polynomial. The general form of such a polynomial is ax plus b, where a is not equal to 0. The maximum number of terms is 2. For example, x plus 1 is a linear polynomial. A polynomial of degree 2 is called a second degree or quadratic polynomial. Its general form is ax squared plus bx plus c, where a is not equal to 0. It has a maximum of 3 terms. For example, x squared plus 2x plus 1 is a quadratic polynomial. A polynomial of degree 3 is called a third degree or cubic polynomial and is represented as ax cubed plus bx squared plus cx plus d, where a is not equal to 0. Such a polynomial can have a maximum of 4 terms. For example, x cubed plus 3x squared plus 3x plus 1 is a cubic polynomial. Similarly, any polynomial of a degree greater than 3 is named on the basis of its degree, such as 4th degree polynomial, 5th degree polynomial, and so on. In a polynomial with one variable, the value of the variable where the value of the polynomial becomes 0 is the 0 of a polynomial. In other words, the value of x for which the value of the polynomial equals 0 is the 0 of the polynomial p of x. Let's take up a problem as an example. Find the values of a linear polynomial p of x is equal to 2x minus 4 at x is equal to 1, minus 1, and 2. Let's solve the polynomial for each of these values of x. First, substitute x with 1 into the polynomial. The value of the polynomial is -2. Similarly, the value of the polynomial for x is equal to -1 and x is equal to 2 is -6 and 0 respectively. In this example, the value of the polynomial is 0 when x is equal to 2. Therefore, 2 is the 0 of the polynomial. P of x is equal to 2x minus 4. In general terms, if P of x is a polynomial and k is a real number, and if P of k is equal to 0, then k is called the 0 of the polynomial. You can determine the 0 of a polynomial through two methods, by trial and error and by equating polynomial to 0. Consider a linear polynomial. P of x is equal to 2x plus 4. Let's first use the trial and error method to find the 0 of this polynomial. To begin with, let x is equal to 1. Substituting 1 in the polynomial, you get 6, which is not equal to 0. If x is equal to -1, then the value of the polynomial is 2, which is also not equal to 0. Try using another value, 2, as the value of x. The value of the polynomial is 8, which is again not equal to 0. In the fourth try, you use -2 as the value of x. You will find that the value of the polynomial is 0. Thus, using the trial and error method, you can determine that the 0 of the given polynomial is -2. As you can see, the trial and error method can often be long and tedious. An easier way to determine the 0 of a polynomial by using the other method, that is, equating the polynomial to 0. In this method, you can find the 0 of the polynomial P of x is equal to 2x plus 4 by taking x as the subject. Thus, P of x is equal to 2x plus 4. P of x is equal to 0. Thus, the value of the polynomial 2x plus 4 is equal to 0. On solving, you get x is equal to -2. This indicates that the value of P of x is equal to 0 if x is equal to -2. Therefore, -2 is the 0 of polynomial P of x. Thus, you can obtain 0 of a polynomial by equating it to 0. Here is a simple problem that involves division. John has 7 apples. He shares the apples with his friends, JC and Jill, so that all 3 of them get an equal number of apples. How many apples remain with John? To find the remaining number of apples, you need to divide the number of apples by the number of people. You can do this through the division rule. Each one of them gets 2 apples, which means 6 apples are distributed. Therefore, the remaining number of apples, or the remainder, equals 7 minus 3 times 2, which is equal to 1. As you can see, it is easy to perform these operations with integers. However, if the number of apples and recipients were polynomials, such as 8x squared minus 3x plus 5 and x minus 2, then the remainder can be calculated quickly and easily by using a theorem called the remainder theorem. Welcome to the lesson on remainder theorem. At the end of this lesson, you will be able to state the remainder theorem, verify the remainder theorem, and apply the remainder theorem. The remainder theorem states that if P of x is a polynomial in x and P of x is divided by x minus a, then the remainder is P of a. Let's now see how we can verify this theorem. It is given that the dividend is equal to P of x and the divisor is equal to x minus a. Let the quotient be q of x and the remainder be r, On the basis of the division rule, you can derive the equation P of x is equal to x minus a times q of x plus r. This equation is true for all real values. Therefore, if we assume x is equal to a, then P of a is equal to a minus a times q of a plus r. On solving, you get r is equal to P of a. Let's now apply the theorem to solve our problem. In the problem given at the beginning of this lesson, the dividend is equal to 8x squared minus 3x plus 5, and the divisor is equal to x minus 2. Let P of x is equal to 8x squared minus 3x plus 5. Now, according to the remainder theorem, if P of x is a polynomial in x and P of x is divided by x minus a, then the remainder is P of a. Therefore, in this problem, the remainder r is P of 2. If you replace x with 2 in the polynomial P of x, you get the remainder r is equal to 31. Remainder theorem states that if P of x is a polynomial in x and P of x is divided by x minus a, then the remainder is P of a. The remainder theorem specifies the remainder in cases where the divisor is x minus a. However, there may be cases where the divisor does not appear in the form x minus a. In such situations, you can use the following guidelines to determine the remainder in the division of a polynomial. If a polynomial P of x is divided by x plus a, then the remainder is P of minus a. If a polynomial P of x is divided by ax minus b, then the remainder is P of b divided by a. If a polynomial P of x is divided by ax plus b, then the remainder is P of minus b divided by a. Let us apply these guidelines to solve some problems. In the first problem, you need to find the remainder when a polynomial minus 8x cubed plus 4x squared minus 2x plus 7 is divided by another polynomial x plus 1. Here, the divisor is x plus 1. According to the guidelines provided, if P of x is a polynomial in x and P of x is divided by x plus a, then the remainder is P of minus a. Therefore, in this problem, the remainder is P of minus 1. If you replace x with minus 1 in the polynomial P of x, you get the remainder is equal to 21. In the next problem, you need to find the remainder when a linear polynomial 2x minus 1 divides another polynomial minus 8x cubed plus 4x squared minus 2x plus 7. As given in the problem, the dividend is equal to minus 8x cubed plus 4x squared minus 2x plus 7, and the divisor is equal to 2x minus 1. According to the guidelines provided, if P of x is a polynomial in x and P of x is divided by ax minus b, then the remainder is P of b divided by a. Therefore, in this problem, the remainder is P of 1 divided by 2. If you replace x with 1 divided by 2, in the polynomial P of x, you get the remainder is equal to 6. Consider another problem where you need to find the remainder if a linear polynomial 2x plus 1 divides another polynomial minus 8x cubed plus 4x squared minus 2x plus 7. According to the problem, the dividend is equal to minus 8x cubed plus 4x squared minus 2x plus 7, and the divisor is equal to 2x plus 1. According to the guidelines provided, if P of x is a polynomial in x and P of x is divided by ax plus b, then the remainder is p of minus b divided by a. Therefore, in this problem, the remainder is p of minus half. If you replace x with minus half in the polynomial p of x, you get the remainder is equal to 10. Welcome to the lesson on factor theorem. At the end of this lesson, you will be able to state the factor theorem and apply it to factorize polynomials. A polynomial is an algebraic expression consisting of multiple terms of variables and constants. These terms are combined by using mathematical operators, addition, subtraction, and multiplication. The exponents of variables must be whole numbers. A term can be a variable, a constant, or a product of the two. A real number that precedes the variable is called the coefficient. The variable of this polynomial is x. Hence, it can be represented as p of x, which is the general form of representing polynomials. In this polynomial, the highest degree of x is 2. Thus, this is a quadratic polynomial. Now, let's factorize this polynomial. Here, we will write the polynomial in the form of this algebraic identity. This method of factorization of a polynomial is also known as splitting the middle term. The factors of this polynomial are x minus 2 and x minus 3. Now, we'll substitute x equal to 2 in the polynomial. We get p of 2 equal to 0. Similarly, we'll substitute x equal to 3 in the polynomial. We get p of 3 equal to 0. Based on the above discussion, we can sum up that p of 2 is equal to 0 if and only if x minus 2 is a factor. Similarly, p of 3 is equal to 0 if and only if x minus 3 is a factor. Let's generalize this for any real value of x. Consider p of x is a polynomial and a is a real number. If p of a is equal to 0, then x minus a is a factor of the polynomial. This is known as the factor theorem. This theorem is an extension of the remainder theorem. If the remainder becomes 0, then you can say that x minus a is a factor of p of x. Conversely, if x minus a is a factor of p of x, then p of a is equal to 0. The factor theorem can be used to factorize a polynomial or verify that a linear polynomial is a factor of another polynomial. Let's factorize this quadratic polynomial using the factor theorem. we'll find the factors of the constant term -4. Next, we'll substitute the factors in the polynomial. Let's begin by substituting 1 in the polynomial. Here the polynomial becomes 0. Based on the factor theorem, we can say that x minus 1 is a factor of the polynomial. By performing the same for all factors, we get p of -4 is equal to 0. Therefore, x plus 4 is also a factor of p of x. This can also be obtained by dividing the polynomial by x minus 1. The obtained linear polynomials are the factors of the quadratic polynomial. Let's recap. The factor theorem states that p of x is a polynomial and a is a real number. If p of a equals 0, then x minus a is a factor of p of x. The converse is also true. Welcome to the lesson on factorization of polynomials using algebraic identities. At the end of this lesson, you will be able to identify the third-degree algebraic identities and derive the third-degree algebraic identities. You will also be able to apply these algebraic identities to factorize cubic polynomials. You must be familiar with the algebraic identities of second degree listed here. These identities can be used to factorize quadratic polynomials. For example, consider the quadratic polynomial x squared minus 1. Which of these identities can be applied to factorize this polynomial? This can also be expressed as the difference of two squares. Hence, you can use this identity to factorize the quadratic polynomial. The obtained linear polynomials are the factors of the polynomial. Now, we'll consider another polynomial. The highest degree of this polynomial is 3. Hence, it is a cubic polynomial. How will you factorize this polynomial? We know that a cubic polynomial can be factorized by using the factor theorem. You can also use the algebraic identities involving third-degree terms to factorize a cubic polynomial. The polynomial must be in the form of whole cubes, sum, or difference of cubes. Let's derive the first identity. We'll consider the left-hand side of this identity. This can be expressed as shown. Now, we'll expand the second term of the expression by using this identity. Let's simplify the obtained expression. This is the first identity. This identity can also be expressed as the sum of two cubes. You can use a similar approach to derive the second identity. You can express this identity as the difference of two cubes. Please note that we will not derive the third identity as it is not in the scope of your syllabus. However, please remember this identity. You may have to apply this identity for factorizing polynomials. Let's go back and review the cubic polynomial that we have to factorize. We'll rearrange the polynomial. Now, the obtained polynomial is similar to the expanded form of this cubic identity. Let's compare the polynomial with the identity. Hence, the polynomial can be expressed in this form. The factors of the polynomial are shown. Let's recap. The cubic polynomials can be factorized by using the following algebraic identities involving third-degree terms.